Okay, thank you. Yeah, welcome to the next talk about system transparency as a data center security architecture. My name is Christian. I'm working at Elements. I'm actually the head of the firmware development, and with me is my colleague Philip.
Hey. I'm more the open source firmware strategist and also moving out of the company for some other work. But yeah, still being here for the OSF effort. Yeah, so let's get started. First of all, we will look in a short introduction to system transparency. Then we will definitely get into details about system transparency itself, what it is, what it does. And later on, we will also present a short information about the reference implementation we did, and we will also have a demo here. Next slides, please, Chris.
Yeah.
Something? Okay. No, it happened. Yeah, so first of all, a data center or hyperscaler normally requires openness and transparency in the data center. This is probably not always the case, but it's really important to have, especially for open system firmware and also other components. And the operators of those data centers need to control over the fleet, right? So the fleet itself needs to be maintainable, secure, and efficient. And also, there might be end users. That depends on how you see end users. So normally it can be that they are also operators or some other people inside the company. It can be that you're running some service and you want also to show that your end users, which are using your service, how open and transparent you are, so they can trust your service, right? So these are two different motivations, but they are the same goals. In total. That means trust is really important. And so we come to system transparency. So trust is normally facilitated by security. That means we use security in order to enforce transparency and to make trust possible. So trust can also be built up in a different way, that you have contracts, for example, and specific relationships, business partners, right? So, but in a technology world, it's always hard to gain trust. And so we use security technologies in order to make transparency possible. Next slide, please. So what is system transparency? So system transparency itself is a specification. It consists of 7 concepts. Which are more like, let's say, a guideline how you could implement system transparency for yourself. The first of all is a provisioning ritual, which is the initial provisioning of the system you want to use with system transparency. Then we have the integrity protected firmware, which is important, right? So we want to be sure that the firmware stays the same and there are no attackers, and also can somehow show what the firmware consists of. And temper resistance is important in terms of the root of trust. So we want to have a root of trust, which is temper resistance. It can't be modified easily. We want to use reproducible builds, which is really important, because if with reproducible builds, you can just compile the code and compare it to the binary, and it stays the same. So you can verify that the code matches the binary, which is also really important for later on verification. And we use platform attestation, also known as remote attestation, where we can attest that the platform is in a specific state by the integrity protected firmware. There are also two other concepts called limited system access, which is more like for immutable infrastructure, that administrators or operators can modify things in a running system, but we will just ignore that for now. And the most interesting part of system transparency is software transparency, which is basically similar to certificate transparency, which is a concept of Let's Encrypt. So probably you have heard of the Let's Encrypt certificate service, which is used everywhere, or nearly everywhere now in the internet. And the idea is that you have some append-only lock, which is similar to a blockchain, where you can log specific information about certificates. In our case, with software transparency, we log the entire boot process. So we put hash values of every part which was executed into this log and make it publicly accessible. Yeah. Under the hood. So how does it look like? So first we have an initial state where we have a provisioning ritual where we have to set up the hardware. We also have a TPM, which is then tamper resistance, for example. We can also use any other trust anchor technology, to be honest. And we have integrity protected firmware, however that looks like. If that's any flash protection mechanism or boot guard or whatever kind of technology, which is probably open, so that depends what you use in terms of platform features. If you want to have it real open, probably something like SPI flash protection is a good idea. And then we have a hardware initialization, which is done by open system firmware. This can be done through Core Boot or Mint platform, Tiano Core, whatever you use. And later on, you have a bootloader implementation, which is executed. It's also part of the firmware. And what it does is it does a signature verification of a netboot package. Yeah, this is already well known, so a lot of people do that. It consists of multiple signatures, so that multiple parties can sign it and verify it multiple times. Makes it more, or let's say better in terms of if something goes wrong, that if multiple parties signed it, we can verify that not only one person signed it, and this helps in terms of security. Also, this OS package, which is provided via netboot, is basically executed then, and it's only running in memory. This is the best case because then you don't have any state left later on a hard drive, for example. You can also put state on a hard drive, but this is probably not always a good idea, or at least encrypt it in some way and secure it. Yeah, and we have the limited system access. This is probably a nice to have feature.
Okay, even though Philip went pretty well over the implementation details already, let's scope out these a little bit further. So let's have a look into the platform identity, the trustworthy initial state that Philip talked about. Transparent software is actually one of the major things that needs to be in place in order for system transparency to work. And of course, the auditable boot. For the platform identity, we use a well-known chip, which is nowadays most of the time soldered on the boards already. It's a TPM chip. The TPM does contain a certificate and a private key, which cannot leave the TPM anymore, and thus can be used as the platform identifier. The TPM also gives us the ability to use a feature called measure boot, which should also be well known now. That, for example, is the log of a measured boot process from Core Boot. What happens here is more or less that everything that gets executed without the boot process gets measured into the TPM. The auditor later on can extract that log and do remote attestation with that. But that actually gives us the trustworthy initial state. Another thing which is very important is transparent software. So open source software is not mandatory, but it's highly recommended. But what is really mandatory is reproducible builds. Reproducible builds means that the same code can get built on different machines or to different times and has to result in the same bit exact copy, right? So if I build the same code and Philip would also build the same code, this has to be a bit exact copy of each other. Open source, as I said, is not mandatory, but of course the source code must be auditable by the auditor. So using open source code here is just logical. So how does it work? As Philip already stated, our reference implementation StBoot uses an OS package. That is a common known principle used in data centers or at hyperscalers, where you net boot an OS image and boot into that. Here that our OS package does contain, besides the Linux distro that we want to boot, does also have some metadata in it, and it is signed. We use an M out of N signatures verification scheme. That means that M signatures have to be in place. That means practically that, for example, you can apply a rule that if you have five administrators in your infrastructure, at least 3 of these need to sign an OS package in order for the StBoot reference implementation to boot that package. Once this OS package gets generated by the tooling, which is also open source, the hash value needs to be appended in an append-only transparency log. For that, we do piggyback on the Let's Encrypt certificate transparency log. That means for every OS package, we do create a certificate and append that to the certificate transparency log. That certificate then contains all the hash values and information that are needed for you or for the auditor to check if that what he or she built locally on him or her computer does actually these hash values that actually match whatever's in the certificate transparency log. If the platform boots up, all the code and the data which gets executed will be measured in the TPM, and the auditor, of course, can then fetch the PCR values, which get signed by the TPM, and do remote attestation, right? So that's the basic platform attestation process. But that is all theory now, and as we said now a couple of times, we made a reference implementation called StBoot. And maybe Philip can talk a little bit more about that.
So yeah, StBoot is a reference implementation of our concepts. So we decided to do that as part of a Linux boot distribution. So it's currently upstream. You can look at it. They're also on the system transparency homepage where you can later get the information from. You can find a lot of information how to set it up and do it yourself. At the moment, we are OSF compliant. So I will come later to it, why we are OSF compliant. So basically everything is open source and you can use it. This is also the same for the software transparency log. And the bootloader implementation is written in pure Golang, so which makes it nice to integrate and root and Linux boot together. Yeah. The scenarios, how you can use it to integrate it into your platform is you can use it as firmware payload, so you can put in the StBoot Linux boot package into your UEFI or core boot firmware. You can run it as UEFI application, so you can compile the Linux boot kernel as UEFI stub, and so you just launch it after the UEFI firmware started, or you can also use it on legacy systems. So for all of these parts, we made sure that signature verification and measured boot is possible from the firmware level. So everything which is measured already then is secured. And this means the execution flow shouldn't have any holes, and you can just use it out of the box. The best experience, the best experience in general, just to let you know, is with, for sure, open system firmware, where you have most of the parts open, because this also increases experience with trusted computing / remote attestation itself. Yeah, now we have a demo. Chris, can you show it?
Yeah. Let me just play that here. Yeah, what actually boots up now is the mixed firmware scenario that Philip just talked about. And we are booting into Linux boot with uroot. And as an init command, we do start our StBoot bootloader. Here you can actually see that we do download the boot ball, which does contain some metadata. Scroll up a little bit here. It does contain some metadata and, for example, here a label on how that is so called, Linux kernel, InnoDrumFS, command line, etc., etc. There were 5 signatures found, and all of these 5 were valid, even though 3 have been required, so that this M out of N verification scheme. And once that is okay, the bootloader loads the kernel in InnoDrumFS and boots into the Linux system. So at the very end, we do hit the login shell, and off we go.
Yeah. Aside from that, there are for sure definitely different other feature components like init.txt support, where we didn't talk about it because we don't want to put the presentation with too much information in it. So, but you can figure that out through the homepage itself. Yeah. Can you switch slides? Yep. Thank you. And yeah, if you want to get in contact with us, just go to the System Transparency homepage. We also have a Slack there. You can just join the Slack then. There's a link, and you can also find our source code on linuxboot.org and get in touch with it. Yeah, thank you for listening.
Thanks.
Thank you. That was really neat.
All right. Looks like there are no questions right now. Maybe we can go a little bit deeper in what is actually planned for system transparency. Yeah, as Philip already said, we are planning on integrating more security features also. Right now, it is already possible to boot StBoot also with StBoot included, so that we're running TXT on the platform, and then start the tboot hypervisor, which then sets up the DRTM and then boot into tboot. That is one thing that is planned. Also, the StBoot bootloader will be run in production by end of year. So that is not only a concept that we made up theoretically, but that's also already practical in use.
And Christian, what's the platform for tboot? What platform are you guys bringing up? With the
tboot works right now on a Coffee Lake platform here that we have, and we developed that together with one of our customers. So it's not an OCP platform.
Yeah, but you can use it on every OCP platform in theory. We have a test suite, right, where we talked before about the Converge Security Suite. And this is basically run through an API before the system transparency launch is done. And that means we can verify in Linux boot if TXT is supported, and it should work on every TXT capable and tested platform. So whatever it is. So this is because we're working on the Linux boot side. This is quite agnostic for all Intel platforms. Yeah.
Right. So I'm going to ask the same question that Ron was asking me. What is the best way for developers to, how do we support the developers to, contribute to, platform, the capabilities that you're talking about, like platform root of trust, CBNT, TXT. Right. How can we help the developer community for the development without them actually, spending boatload of money for buying the server platform? Is there something we can, take advantage of your infrastructure for development as well? on a time slice basis or something of that sort?
Yeah, so so without buying those platforms, I mean, that depends. So for system transparency, Linux boot is always possible to get a cheap hardware, right? So which is not really costful, and you can also execute it inside a virtualized environment. So system transparency, for example, runs in QEMU, which makes it easy to use for developers. And we also writing down an extensive documentation on GitHub. So this is always helpful. So the most important things, I think, if you want to get in touch with the project, are the communication to the developers, which is done for us at Slack. There should be tons of documentation which are in a good shape, right? And also it should be somehow testable in a virtualized way. And this is definitely possible with system transparency yet. And I guess also for open system firmware yet for Linux boot and some other projects.
Yeah. Oh, okay, super. Yeah, I mean, maybe some sort of a documentation maybe for the developer consumption would be useful on how they can actually use this.
Yeah, for sure. We could also probably later have a follow-ups. I mean, we are all available through the open system firmware Slack and also on the system transparency Slack. But yeah, for sure, we can probably provide some follow-up and how to get into that stuff.
Yeah, that'll really help. Thanks, Philip.
Okay, there's another question. So can you talk about StBoot versus Linux integrity measurement architecture? Yes. IMA is basically developed by IBM, and it's starting. It's a Linux kernel. For sure, this is a technology you can use in Linux boot. But our goal was to use those software transparency log. And for example, system transparency provides this type of log as an implementation, which is also hard to set it up. So we trying to bring it down that you can use it and easily build it. This is one part, and we have also different other parts. So StBoot is just measuring stuff, and for sure there can be additional measurements through the integrity measurement architecture, but they are probably not needed because in a Linux boot case, there's only one application which is loaded. And so it's probably not that useful. And it's also enforced through the kernel, and you can't do net boot loading, right? So in theory, we could just ditch the measurements inside StBoot and let IMA do it. But the question is if there's any benefits. So I think the amount of work you need to set up IMA, which is also not that performance full, or let's say it's not really efficient, is probably not the right way to do for just one measurement we need from the Linux boot side. So we just measure the executed netboot OS package because nothing else is executed. And the Linux boot part is already measured by the firmware. I hope that answers the question.
We go to the
Okay.
panel now? Oh, we have another minute.
Yeah, we have another minute, but we should wrap up. So yeah, please proceed.
Thanks.
Thanks.
Okay, thank you. That's excellent. It's been a great day for talks, I got to say.